So here is an application of integrals. Up till now, we've just become really good at doing integrals. I hope that yesterday's class, where you worked together, was really helpful for developing your skills in being good at integrals. So one of the applications of integrals is finding areas under the curve. Now, a very long time ago, mathematicians like Archimedes came up with this quite simplistic idea of, hey, if I want to find an area under a curved region, that's hard. But if I break it up into little rectangles, those little rectangles will give me a good estimate of the area. In fact, if you look at the diagram here, all of those little yellow rectangles will all be slightly smaller than the actual area. Because you can see a little bit of the white space or gray space that doesn't get hidden into that. But if I made my rectangles smaller and had more of them, right, then my estimate would be better, right? Because my first estimate, oh, I'm going to do one rectangle. That's not a very good estimate. That one would be too big. Oh, I'm going to do the rectangle smaller one. Well, that also is not a very good estimate. Right? Oh, then, yeah, I could do that. I mean, there's different ways you could break this up to get a good estimate. But the idea was, what would happen if I figure out a bunch of little rectangles? So we start with a thought experiment of this. Okay? We're going to zoom in on one of those little rectangles. Okay? And I'm introducing some notation here. This is delta A. Okay? To represent the area, the actual area of that section with the curve. Okay? In this box, we've got a little section of x, being the width of that rectangle. And for y, I've got two different measurements. I've got a measurement up to the curve at its lower point, which I'm going to call y, because that's the actual y value. And then the change in y from to the top of the box where the curve hits later on. So as you make x smaller, so if I made x smaller this way, does it make sense that then the y would only go, the change in y would only go that way, and so both dx and dy, or delta x and delta y would become smaller, and the area would become smaller as well. But from this little diagram, we can set up an inequality. We can say that the actual area, which is shaded, is somewhere between the smaller rectangle, represented by length times width. Are you okay if I underline this in red? Are you okay with seeing that as this red box? And this one, purple, would be this box. Not bad. Different colors. You can still see the red, still see the purple. And so the actual area is somewhere between the area of the red box and the area of the purple box. No problem. And so we continue this thought experiment, and we say, dividing everything by that delta x would create this situation. That y is less than delta a over delta x is less than y plus delta y. Now, this delta a over delta x, that represents an average rate of change with respect to x. And the idea is as x goes to 0, this becomes the instantaneous rate of change. And so if it becomes the instantaneous rate of change, we know that the instantaneous rate of change is the derivative. So as x goes to 0, dx goes to 0, this becomes dA dx. And as dx goes to 0, if we look back at our diagram, as you make this part go this way and become less and less, so too would this become less and less. So your delta y would also approach 0. And if delta x approaches 0 and delta y approaches 0, then our inequality all of a sudden becomes this. Y is less than dA dx is less than y. Now, have you ever had an inequality like that before? If I put a number in there, what does that tell us? Y has to be 3. Like that's the only possibility. Y can't be. Well, 3 is not less than 3. I guess there should technically maybe be equal signs there, right? And we could probably add them into here as well to be even more clear. Okay? And then we can conclude that dA dx is equal to y. Now, dA dx is equal to y. Another thing that's looking at, if we look at our diagram, is if you make the box small enough, your instantaneous area is just basically that thin line. Like it's like a rectangle with a minuscule width. Okay? And yet if we integrate both sides with respect to x, what do we get? We get on this side, well, the opposite of a derivative, integrating and deriving would just end up getting you the area. Plus c. And over here, it's saying that the area is equal to the integral. Which is a really cool result, because we've been doing integrals all the time. How do we then apply this to areas? So what this formula will do is it'll give us the area of something up to a value, from the origin up to a value. So if I take something like y equals 2x plus 1, that is something relatively simple that we can graph. It has a y-intercept of 1, a slope of 2, and would look like this. And if I wanted to find the area between 0 and 1, well, I could do that using my old techniques, because can you see that this makes a little rectangle on the bottom, a little triangle at the top? You could use area formulas that you already knew to figure this out. But let's look at what happens when we calculate the integral of 2x plus 1 dx. And with a definite integral, one of the things we're going to add is some notation. I'm going to figure it out between 0 and 1. What's this integral going to be?
X squared
plus x. X squared plus x. And there would be, when all of our indefinite integrals have had plus c so far. Well, there could be a c. Okay? You could put whatever you want. We're going to find out with the definite integral that the plus c doesn't actually affect anything. Because what's going to happen is you're going to plug in 1. You're going to plug in 1, and then you're going to plug in your lower value, which is 0, and subtract them. Now, in this case, plugging in the 0 will just make everything 0 here. And when you subtract the 2, the plus c's would go away. And in a sense, it doesn't actually matter. So when we do a definite integral, we won't be having to worry about the plus c. And we'll do enough definite integrals so when we get back to the indefinite integrals, you'll forget to write plus c. Well, you will definitely find out in a second. Excellent. Okay. And so if we plug in 1, what is 1 squared plus 1?
2.
1 squared plus 1 is 2. Now let's actually calculate the area of this section. If I calculate this box, would you agree that the area of that box is 1?
Yeah.
And then we have a triangle that has a base of 1, a height of 2. The area of that part would be 1, and 1 plus 1 would make 2. So we could figure out that area by just calculating it. We could also figure out that area with our integral. And so what this does is I can put in other values. If I want to find it, say, from 2 to 3, that would figure out over here this area underneath that curve from 2 to 3. And what it will calculate is it'll calculate the area from 3 all the way back to 0. And then we'll calculate the area from 2 all the way back to 0 and subtract it, ending up with just that area between 2 and 3.
Try to calculate an area where the area is underneath the...
What happens when you try to calculate an area where the area is underneath the curve? That's going to come up, and the area will show up as a negative value. Okay?
No, I mean,
Like what underneath the axis. So, for example, a sine curve looks like this. It has some area here, some area there. That area that's below will show up as negative.
the area only counts to the x-axis, right? No, it doesn't go.
So as Riley was so aptly trying to find out what, because I keep referring to it, it's what is called the definite integral. Our other integrals were indefinite integrals. Well, we are unsure because of the plus c. It could be something else there. A definite integral finds the area, and you know that that's the area. It's not like, I think it's the area plus or minus 500 centimeters cubed, or, right? This is the answer, and I am definitely right. I'm sure of it.
Wait, so an indefinite integral can't tell you what it is exactly, like, it has an uncertainty of
Plus c.
infinity. Well, yeah, what if c approaches infinity? If you just know the area under the curve, but everywhere, it's not very certain. You know the area everywhere. It's just a lot.
So we've got a lower limit and an upper limit to your definite integral, and this will calculate the area under a curve. So the steps for finding your definite integral, you will start by finding the indefinite integral, but you won't worry about the plus c. You'll put that value in brackets as notation-wise, and put your parameters, what your lower value was, a, to what your upper value was, b, there. You will then plug in your upper value, subtract your lower value, and you get a numerical value which will represent the area under that curve. Yes?
Why do you use the upper value subtract the lower value?
Well, it's that idea of, and you can see it with this 2x minus 1. Let's say I want to find the area here between 2 and 3. You will find that I really enjoy using crayons to shade an area. So I will use a lot of crayons in this part of the unit. Okay? If I want to find that area, well, the integral, when I plug in 3, it finds the area all the way down to the origin. When I plug in 2, it finds the area all the way down to the origin. So if I take the upper value, which is the big area, and subtract the lower value, which is that red area, what am I left with but the crayon shaded area that I end with? Now that, in this example, is very simplistic. Sometimes you're going to find that certain values don't quite work as simplistic like that, but the idea works either way. So in other words, we figure out our integral, set up our values, and then subtract. What's that?
Those don't look like words to me.
In other words, in other symbols. Yeah, it's in other symbols. This one here.
Yes.
Is your plugins up there? For charging?
Yeah.
It just says, well,
You know what, Ramsey? You're right.
This one might be different.
Good question, Gabe.
No.
I charged this one.
Where does this one go? There it is. That's the one we're looking for.
this is not the charger you're looking for.
Okay.
You don't have a battery?
So let's think about this next example. And this is really fun, in my opinion. I do like math. But when I'm graphing 3 over x, would you agree that that is a 1 over x graph? Has an asymptote here, an asymptote here. You plug in some points. There'll be a vertical stretch by a factor of 3. There's your 1 over x graph. And what this question is asking us to figure out is with this curve, from 2 to 5, pull out our crayons.
Love crayon.
Can I borrow yours?
Oh, look at that. That's fun.
Make it darker. Make it darker.
Oh yeah,
Like a real crayon.
it is like a real crayon, and if you use enough imagination, you can smell the wax.
Does it taste like it?
They all have
Okay? So that is the area that we're trying to find. And before this, trying to get an estimate for that, you could probably do that. But if you had to try to find that area before today's class, you go, oh, that would be hard. Because it's curved, it's weird,
Beautiful.
it's beautiful.
Let me tell you this about on one of the IB physics exams, there was it was a certain like it was a weird shape like that.
Yeah.
And you had to count the boxes that were in it. They were tiny. There was there was over 100 boxes in it, and you had to be within 2 to get the points.
You just had to count the area. I mean, that, I kind of don't mind that as like, that's a basic way of figuring out area. You take a grid, put it over top, and count boxes to your best estimate, right? And the smaller your boxes are, if you do a 1 millimeter grid, you're going to be more accurate. But
What was it? Then you had to count like partial boxes. You had to get within 2, and there was over 100 boxes.
so our setup for solving a definite integral is, first of all, you're going to integrate. What would you get if you did the integral of 3 over x? 3 natural log of x.
I actually got it.
You got it. I mean, what we did yesterday was helpful for figuring out integrals. And then we'll put our parameters that you're going from 2 to 5 there. And then to evaluate this, you'll plug in your values. So first we'll plug in 5, and then you'll plug in 2.
Where's the calculator?
So you could simplify this. I mean, I could factor out a 3, natural log of 5 minus natural log of 2, which is equal to 3 natural log of 2.5. Right? Log laws.
Oh, no.
Could you then put the 3 up and square it?
Yeah, you could put it all inside if you wanted to and have 125 over 8. However you would like to play around with this.
I feel like you're just showing off now. This is true that you're not making this up.
Those are right numbers. Yeah.
Mess around for the entire class. Jokes on you, we're starting to get more around.
Log laws. Do you know how I got from here to here?
No. Oh, you divide it.
Divided, right? There's not a new log law that the negative sign becomes a decimal place and you switch them. That would be... Okay. But yeah, you divide 5 divided by 2. And then the 3 goes in as cubing. So 5 cubed is 125, 2 cubed is 8. So done.
I thought it was multiplication.
Oh yeah, this is 2.5. And you type that into your calculator, you will get a numerical value. I'm not sure what the natural log of 125 over 8 is. It's not in my mental math capacity yet.
If you take, okay, well, natural log of 2.5, let's say e to something is 2.5.
Hey, good. Well,
Supposed to. Yeah. What about 1? Times 3.
Because it's 2.5 cubed, right? And e is 2.7, so it's going to be a little less.
Oh, no, if you go back, don't do the 125 over 8.
is that area?
It's got to be less than 1. It's like maybe 0.9.
And then you cube it. Yeah. There are lots of ways you could estimate it. But it's really cool because you just found that area, the 2 decimal places, and relatively
Painlessly.
painless, and we've learned some techniques for integration, relatively easy to do. Comparatively to how you would try to figure that out with geometry and stuff. Like even if you put grids down and you started counting boxes, to get to 2 decimal places would be very difficult.
That's the point. Like, why would you want to find an area in the middle?
Because you.
Why would you want to find the area of the middle? Well, we'll get to some applications. Despite the fact that it's very cool, we will get to some applications of where you would want to find areas under
Maybe like
things.
some economics or something. You want this time, you want area.
Possibly.
There's, all right. We don't wait for very long before getting into some nice, challenging, definite integrals.
Like we go from 1 to a much different.
Integral from 2 to 4 of x plus 1 over x. I'm gonna see if you guys can think of what kind of strategy you're gonna do. I'm gonna open up my calculator. I'm gonna graph x plus 1 over x squared just to see how pretty of a graph that looks like. Yeah, integrate that. Are you having trouble?
What was the question?
X plus 1 over x squared.
No, from what? X plus 1 over x.
Squared. The entire thing squared.
And
You can integrate.
what are the bounds?
From 2 to 4. There it is. Oh, and then my calculator goes and freezes on me.
The function is out of function, that's when you substitute.
This one is designed for you to want to feel like you want to use substitution. Because you see,
But you can't.
you can't, you're right, you can't use substitution. But you see, no,
The x.
you see a function inside of another function, right? The x plus 1 over x is inside the squared. So you just want to use substitution. But the problem is the derivative of that would be 1 plus natural log of x. No, sorry, 1 plus negative, or 1 minus x to the negative 2 would be the derivative, right? And that doesn't appear anywhere for substitution. So your best option is to think, well, what does 1 over x plus 1 over x squared mean? Well, that means this. And could I multiply that out?
That's tricky, Mr. JR.
I could. That'll give me x squared plus 1 plus 1 plus 1 over x squared. And each of those things separately are easy to integrate. What's the integral of x squared? X cubed over 3. What's the integral of 2? 2x. What's the integral of x to the minus 2? X to the minus 1 divided by minus 1. From 2 to 4.
Well, 30.9. That's why I put the square brackets. What makes the 1 over 2?
What's that?
It should have been 4.
I like it.
Oh, I see. That, the top one looks like a 1.
What is your problem?
And so now we will substitute in the 4 and substitute in the 2 and subtract. So 4 cubed, 64 over 3 plus 8 minus 1 over 4. plug in 2. 8 over 3 plus 4 minus 1 over 2. Often in questions like this, I will, instead of solving within the brackets, I'll distribute my negative. I'll put together easy ones, like can you see 64 minus 8 over 3 will be? 56 over 3.
Yes.
8 minus 4 is 4. And then a quarter plus a half. Negative quarter plus a half will be plus a quarter. And then I'll work at trying to get my common denominator from here. So it's going to be 12. So we multiply this by 4. 224 plus 48 over 12 plus 3 over 12. We're going to get 51 onto that, 271. Just mental math.
That's the area. That's the area. He solved for the area. It's incredible.
I think, is that a mistake in there?
That's a mistake.
Yeah. 275. Yes, there we go. I saw 275 over 12. Yeah, 22.92. Now I'm going to attempt once more to get our calculator working. There is our graph, and I'm going to show you a nice value on your calculator. Second calc, number 7, integration. Push number 7, go from a lower limit of 2 to an upper limit of 4, and it tells us the answer is 22.91.
666.
Whoa, wish I was paying attention.
I don't have a calculator, so I can't.
I was just throwing out my wrapper and suddenly you blew it all over the place.
Wait, is that what this says?
Yes.
Okay, perfect. As long as it's written on the paper.
Okay. Now, what I want to just some things. Oh, this might help you for your IB exam.
Yeah.
Okay. You've got that value. You can now. Let's see if I can get this out here. I'm going to try pushing X right now and see if it comes up as 22.96. No, it didn't. Okay. We're going to go back to our graph. Back to calculating number 7.
How to be weight transfer.
There is a way to transfer. I just have to see if I can remember how to do it.
What zoom did you use?
6.
Oh, shoot.
4 equals 4.
What?
Number
That's
7.
not true.
Lower limit 2, enter. Upper limit 4, enter. We've got our answer. I want to check if I've got it. If I go second answer, does it remember the answer? Yes.
Money time. Now
Okay.
scores X.
And then math fraction it, and we get, 275 over 12.
I like how we figured out the exact.
Why do you know all these cool calculator tricks and smartboard tricks?
Is there one
He is smart man.
I've
Calculator, smartboard,
been
man.
figuring things out.
Is there one for a derivative?
There's no one gets calculator everywhere.
Okay. Pretty cool.
Covered with this. I just realized now it's your
See?
It took me a second.
I apologize.
I do, during the class, do a number of jokes, and some of them never happen. Nobody ever gets them, and I just have to chuckle inside.
Thinking, I'm like, wait, that was clever. I like that.
Which one was it?
Gabe had used vulgar tones and diction artists, which reached to cover his headphones so he wouldn't hear the music.
I got his wrong answer.
Again.
Stupid.
I can help you. I can probably figure it out.
All right.
How'd you get the X's there?
Let us try this one.
That's it's not a calculator question, right?
No.
Just make sure.
Guys, we don't need this out.
Integrate. What would you get for e to the 3x?
It'd be e to the 3x over 3.
Oh, you guys did learn so much yesterday.
I went home and wrote down
What if
everything.
it's e to the u, you don't divide by u?
And this one?
I don't know.
Wait,
I have no idea.
you guys do U substitution. Yeah.
No, you don't need to. You could, but you should be able to.
Oh, wow, yeah.
Oh, gross.
X plus 1 more.
Wait a moment.
There's no chain rule that happens, so you don't really have to worry about it. And then we're going from 0 to 1.
You don't have to write the dx after.
No, in this notation, you've got your definite integral. You've integrated. So now we can plug in 1. E cubed over 3 minus 2 natural log of 2. Subtract, plug in 0. What is this going to be? 1/3. And what is this going to be?
No. 0. Natural log of 1 is 0.
Natural log of 1 is 0. Just to, natural log of 1 is asking e to what exponent would be 1.
That's right. Log sulfur exponent.
And then
That is
you did
right.
third minus 1. Oh. How did you get?
I haven't done math in a long time.
Why are you this fast then?
The other math, not this one. Remember when I couldn't factor anything here?
Can someone type this into the calculator and see if it matches up with 4.976?
My calculator can't handle that. What? No. Why not?
This semester here. Fair math?
It isn't set.
We've got an integral from pi over 6 to pi over 2 of sine 3x. So first of all, we need to integrate.
It's cos of 3x divided by 3.
Cos 3x divided by 3. And you're going from pi over 6 to pi over 2. These are values on your unit circle. It'll be negative cos. Yeah. So close. Good. And what happens when we plug things in? Plugging in pi over 6 will give us cos of pi over 2 divided by 3. Minus, plug in pi over 2 will be cos of 3 pi over 2 divided by 3. Cos of pi over 2 is 0.
So that's 0 minus 0. 0. 0. How? It's not possible.
Because they cancel.
And then you put a smiley face and then.
You're confused. Get really confused what's happening.
Because on the top and the bottom they cancel because they're the same.
So in definite integrals, any area above the x-axis will be positive. So I'll color that here in green. That will be considered a positive area. And any area under the x-axis, which I'll color here in red, becomes negative. And that positive area happens to be, because the cos graph is symmetrical, equal to that negative area, and it cancels out.
The total area is 0, right?
The total area is 0.
Well, like if you, well, what would you call it if you took the absolute value of the bottom part?
That would be a question saying, find the area between the curve and the x-axis. Okay? So if it's a word problem saying find the area between the curve and the x-axis, you would have to break up your integral into 2 sections. Oh yeah, I wasn't paying attention because I knew there was going to be 0, so I was getting a little excited. Good point here. Notation-wise, we did the wrong order here.
That's why I was super confused.
It should have been 3 pi over 2 first, and then pi over 2 second. On a different question, that would be super important. Good point.
I'm passing calculus.
Hey,
Where are you?
you're on your way to passing calculus as a result.
I think we're all because we're smart.
Say that again.
Okay,
So wait, how many people are still enrolled in this class?
2 more for you to try. This one, despite the fact that it goes from 3 to 2, you can still calculate the definite integral. It's from 3 to 2.
So I know they got a negative.
Hey, shouldn't do it.
Oh no.
There's your first one. I picked a new color.
That looks bad, like it's like actually so in between looking like it should be brown, black.
I want to.
Is that burgundy kind of?
There.
It looks like a little bit like wants to be red.
Yeah.
But not
There it
very
is.
much.
Like red and brown. I like how we're judging them.
I like this. This is aged ketchup.
It's really hard to like,
You don't like that color?
My eyes, they're dying.
No, it's
actually looking at
okay. Well, let's adjust it a little bit lighter, a little bit more purple. Is that better? No, it still needs to be somewhat.
Trash.
Maybe a little bit in there.
That looks horrible. What are you?
It's a mauve accents.
No.
No, I don't. I like that.
That looks like someone puked it.
There we go.
That looks like someone's tongue.
That's better.
That looks like someone's tongue. Try it. That's exactly the same. You have to click OK.
Okay.
Click OK.
Yeah, that's definitely not so smart.
Oh, that
it is though.
definitely a little bit better. Not quite as dark.
Jeez. God.
Not. You want to work on that one?
Change.
Okay, a little bit. It's still too dark. Right there.
That's orange.
That's too red. It's got to be significant. It's got to be enough different.
That's gonna say.
It's a little bit lighter.
Oh no, it's.
Cannot
Right.
tell from back here.
See, you need it to be different than red, so I can have a new color. Right?
Please stick with
So many other colors that you can pick.
Yeah. Well,
Actually,
I got to change this green one too.
we're good.
How about gray or white?
Orange.
Cyan.
You like that orange?
That's actually
That's not bad.
Beautiful now.
I'll save that one too.
Oh, it looks like
There we go. Is this one still working? Or do I have to reset that one?
that one's good.
You like that one?
So the answer is equal to negative 1/5. Awesome.
Oh yeah, there's the answer, negative 1/5. Meanwhile, all that pen stuff will be nicely on the video while you can.
Well, exclamation
Yeah,
point.
that's the best part of class. Anyone who misses class, that's what they're here for. They're not learning integrals or anything. They're here for this talk.
For the interesting stuff.
The calculator talk, the photo talk, and the color talk.
Okay, have you done this one?
Basically.
Oh, what?
Gabe, what the heck are you doing there, buddy? Catch up.
Oh, what colors?
I yelled at them. That was a very, very nice yellow.
Wait, we get food?
No, I don't know who left these in here. I hope they're edible.
Are they jelly?
It must be Mr. Rohringer.
Really good?
Do you remember when Mr. Rad?
I want to see it.
Please show us.
He brought us
Look
like
away.
5 bags, and then he used like half a bag, and he was like, "Oh no, oh no, what am I gonna do with it?"
3 minus 1
He's like,
over
I don't want this many
Why
bags.
is it
40.
Why is it plus?
You shrugging?
What?
Yeah.
You're right.
Sure.
Why did it become plus?
Because when you multiply, because the negative 1 in front of the x is the coefficient of e, right? So
I don't know
when
if I have
you're
enough
doing the opposite,
Here.
wait, why is it really the negative?
Simon, what's this? The office from us?
Oh no, Simon's in trouble.
Times a life divided by negative 1. The actual is 1 over a.